And at first, I'd like to thank organizers for giving me an opportunity to make this presentation today. I'm Takafumi Kamizuka from University of Tokyo, and I'd like to talk about the engineering observations of our instrument MIMIZUKU performed at Subaru telescope in 2018. So at first, I'd like to introduce our instrument MIMIZUKU. And this is a first generation mid-infrared instrument for the Tau 6.5 meter telescope, which was already introduced by Miyata-san yesterday. And we are now constructing this telescope in Chile. And the left panel shows our instrument MIMIZUKU. And this is a little bit large instrument. The size is about 2 meters and weight is about 2.5 tons. And here is the main characteristics of MIMIZUKU. The first one is the wide wavelength coverage. MIMIZUKU has 3 optical channels called NIR, MIRS, and MIRL, covering different wavelength ranges as shown here. And by utilizing these optical channels, MIMIZUKU will cover our wavelength range from 2 to 38 microns. And it will enable us to perform imaging observations and low-resolution spectroscopic observations. And another characteristic is the capability of accurate calibration of atmospheric absorption. MIMIZUKU has a special optical device called field stacker, and it enables us to compensate the atmospheric absorption accurately, and it enables us to perform accurate photometry and spectroscopy. So by realizing this instrument, we want to go to longer wavelength side, and we want to realize monitoring observation from ground-based observatory. And here is a field stacker. This was also introduced by Miyata-san and Mitsubishi-san yesterday, but I want to explain it again here. And the field stacker device is installed here on the MIMIZUKU to place pickup mirrors on the telescope focal plane. And the light coming from 2 fields are reflected by these mirrors and another mirror here. And they are combined into one beam and introduced to the camera system. So by using this mechanism, we can observe two objects in different fields simultaneously, and by comparing them, we can compensate the atmospheric absorption correctly. So this capability will lead accurate observation, important for monitoring. And to verify this concept of the field stacker system and evaluating to evaluate the on-sky performance of our instrument, we brought our instrument to Subaru telescope, and we performed engineering observations in 2018. The first one was done in July to evaluate the N-band imaging observation mode. And the second one was done in December to evaluate Q-band imaging mode and spectroscopic modes. And from here, I'd like to report the result of the observations. The first one is imaging results. These are the images of some brightest sources. The left one is N-band image in logarithmic scale, and the right one is Q-band image in linear scale. And at first, we measure the FWHM of the central quartz, and evaluated values are shown here. By using these values, we evaluate the spatial resolutions. And these values suggest that we can achieve diffraction limited observations by using MIMIZUKU in the N and Q bands. And we also estimated the system efficiencies, and the obtained values are shown here. We think these are in acceptable range. And one strange thing confirmed in the observation is the Q-band PSF. As you can see in this panel, some
you have 2 minutes.
Symmetric. really? Okay. Asymmetric features seen like this, and it can be caused by some troubles on pupil or something like that. And we wanted to investigate the result, investigate the origins, but we didn't have enough time. And next one is the spectroscopic results. We obtained N-band data and Q-band data like this, and the observed target was a planetary nebula M111. And we evaluated the wavelength coverage based on the atmospheric emission lines, and evaluated the spectral resolutions by checking the emission lines from this planetary nebula. One is neon line, and another one is sulfur line at 18 micron. And as a result, we obtained these values, and we confirmed that wavelength coverage and resolutions are consistent with the designed values. The next one is the field stack imaging results, but I will skip this because Michiru-san yesterday already reported. And the last one is a spectroscopic observation result with using a field stacker. And two objects are successfully observed like this, and their Q-band raw spectra are shown here. And you can see some small fluctuation like this, but this is caused by sweet loss. So we can reduce this fluctuation by scaling like this. And after that, we divided this spectrum with this spectrum. And finally, we obtained a relatively smooth Q-band spectrum of the count ratio between these objects. And this relatively smooth spectrum means that we can accurately correct the atmospheric absorption, and we can obtain Q-band spectrum even in the harsh Q-band. And if we go up to the tau site, it is expected that we can obtain high quality Q-band spectrum even from ground-based observatory. So here is a summary of the observations. The MIRS channel in MIMIZUKU was tested, and we confirmed that all functions are working well, and the field stacker actually improves the photometric and spectroscopic accuracy. And we are now preparing other parts of MIMIZUKU for starting the scientific operations from 2022. Thank you.
Thank you, Takafumi, for this interesting and intriguing mode. I have one rapid question. There are more in the Slack, but the first one is by Warren Skidmore, who's asking, how is path length preserved in the field stacker system?
So path length on the field stacker, just a moment. So are you asking this length?
It's basically, my question is, if you move you know, the mirrors, you're also changing where the image is brought to focus down here. How do you deal with that?
Yes, we actually move this cryostat up and down to compensate the focal length change.
Okay, and you keep the midpoint of the targets on the optical axis or something like that?
Yeah.
Okay, thank you.